Alright, hi everyone. Welcome to our video example for multiple units with reactions. In the corresponding lecture, we talked about in general that reactors are not standalone units. Typically what you do is you put the effluent through some kind of separator so you can separate out your products. And as a result, we have different subsystems and we go back to a multiple unit process in that case. We looked at one of the examples during the lecture and now we're going to do a second example. And this is question 4.80 on page 206 from your textbook. So read up on that question first before following ahead with this video lecture. All right, in this question, we have methanol that is synthesized from carbon monoxide and hydrogen in a reactor. We are given that the fresh feed contains CO, H2, and nitrogen, and so we're given the compositions of that. This stream is mixed with a recycle stream. We're given the ratio of the recycle stream to the fresh feed, and this gives the feed to the reactor. And we have the mole fraction of nitrogen going into the reactor. We are told that there's a low single-pass conversion attained in the reactor, which means that the limiting reactant, whichever that is not fully consumed within the reactor. The reactor effluent goes to a condenser, which is our separation unit in this case. We have two streams, a liquid stream that has all the methanol, and in the gas stream has the unreacted carbon monoxide, hydrogen, and our inert, which is our nitrogen. This gas stream is then split into two streams. We have one that is our purge stream, and the other one that's the recycle stream that combines with our fresh feed. So just going through this, you'll see that it's a pretty typical skeleton that we're going to end up drawing that we have drawn earlier in our example as well. So we're given a methanol production rate of 100 kilomoles per hour. We're going to calculate the fresh feed rate, molar flow rate composition of the purge, and the overall and single pass conversions of this entire process. All right, now what I want you to do is just pause this video, draw the skeleton, label the flow chart, circle all your unknowns, and then we'll come back and start to do the degree of freedom analysis. All right, so hopefully you had a chance to try out drawing the diagram. In this case, like I said, it's a pretty typical setup that we have seen before, and this is what you should get. You have a reactor leading into a condenser, and then you have a gas stream that gets, half of it gets recycled and some of it gets purged, and the recycled stream meets up with a fresh feed to give you the feed into the reactor. Double check this diagram with what you have tried on your own to make sure that you have everything that's listed here on this diagram. The one thing I do want to point out that is important here again is the presence of this splitting point right here. In this case, I have labeled my mole fractions of my recycle stream and my purge stream separately, but I've also made a note to say that these mole fractions are the same as the mole fractions in my stream 4 because that's a splitting point. It is important for you to remember to do that because otherwise you will triple count the number of unknowns around the splitting point and you have too many unknowns around there. Alright, so now let's use this diagram that we have labeled and drawn, and we're going to do our degree of freedom analysis. That should give us an idea of how we're going to solve this problem. Again, we have 5 different systems. We have the overall system, condenser, reactor, splitting point, mixing point. Starting with the overall, let's do the molecular species method. I'm always going to go through all 3 methods just so that you are familiar with what we are doing here. Using the molecular species method, we have 5 different unknowns. We have 1 in the feed and 4 in the purge. So that's our 5 unknowns. We have 1 reaction going on in this overall system. And we have 4 different species. We have our hydrogen, carbon monoxide, nitrogen, and our product methanol. So we have 4 species. And we have 1 constraint, so the sum of y must be equal to 1 in the purge stream, or in this case we have labeled it as 4 in stream 4. So in the overall, we have a degree of freedom of 1. Let's double check this with our atomic. Our atomic, we have 5 unknowns, the same 5 unknowns. There are 3 atomic species. They are reactive, carbon, hydrogen, and oxygen. We have an inert, so a non-reactive molecular species. And we have 1 constraint, which is the same constraint that we talked about, sum of mole fractions equals to 1 in stream 4 or the purge stream. But what's going on here? Why do we have a degree of freedom of 0? Once again, this goes back to the fact that with atomic species balances, generally that's the one that causes problems with the degree of freedom. So always double check that with the molecular. In this case, this is something that is, you can actually see what's going on, which is carbon and oxygen are present in the same ratio in all the species. So if you look through all the species where carbon and oxygen are appearing, it appears in carbon monoxide and it appears in methanol. In both of these species, they are in the same ratio of a 1 to 1. So going back to 2 lectures ago when we talked about this idea of independent species balances for atomic, when you have 2 atomic species that are in the same ratios in all the species that are present around the system, they are not going to be independent. So in this case, you'll see that carbon and oxygen are always in a 1-to-1 ratio in carbon monoxide and in methanol. When you write out the carbon balance and the oxygen balance, they are going to look identical. And that's why the C and O balance are not independent. That is why we have a degree of freedom of 0 when we should not have that. We should have a degree of freedom of 1. This is how the degree of freedom for atomic should look like. We only have 2 independent reactive atomic species. Hydrogen itself is going to be independent. Between carbon and oxygen, you can do either or. And again, once we actually start to do the problem, I would encourage you to write out both to convince yourself that they're going to look identical. So we have 2 independent reactive atomic species, 1 non-reactive species, and then a constraint. So that gives us a DOF of 1. The extent, again, I'm not going to write that out because all we're doing is we're going to take out the nitrogen and put it as a non-reactive species. All right, so that's the overall degree of freedom. Let's move on to the reactor. In the reactor, we have 7 unknowns. We have 3 in stream 1, 4 in stream 2. So those are our 7 unknowns. We have 1 reaction. We have 4 species, like we looked at, the same 4 species that we looked at in the overall. We have 1 constraint, the sum of mole fractions must equal 1 in stream 1, the feed going into the reactor. So we have a degree of freedom of 3. Same thing with the atomic, 7 unknowns, we don't have any reactions, 2 reactive atomic species, we talked about this, C and O are not independent, 1 non-reactive species, and then 1 constraint, and so we have a degree of freedom of 3. So that's consistent. All right, let's go on to the condenser. Condenser, we have 8 unknowns, 4 in stream 2, 4 in stream 4. 4 different species, the same 4 species we have looked at, and we have 1 constraint. So the constraint is mole fraction must equal to 1 in stream 4. So we have a degree of freedom of 3. Mixing point, we have 8 unknowns, 1 in the feed, 3 in stream 1, 4 in the recycle stream. That's our 8 unknowns. In this case, we only have 3 species. The methanol has been produced, is not involved around the mixing point. So we only have 3 species. We have 2 constraints. We have sum of y equals to 1 in stream 1 and in the recycle stream. And we're also given a specification. Recall that back in the question, it says that the recycle to the fresh feed stream is 5:1. So we get to use that as well around the mixing point. That gives us a degree of freedom of 2. Lastly, our splitting point, we have the number of unknowns is 6. We have 3 mole fractions and each of the molar flow rates of each of these 3 streams. That's our 6 unknowns. Around the splitting point, you only have 1 independent balance. And then we have a constraint, the sum of the mole fractions must equal to 1 in that stream. So we have a degree of freedom of 4. Once again, we see by looking at all the degrees of freedom, we do not have a degree of freedom of 0. So this again is not perfectly posed. Things are not as perfect as we want. It's just like life. Life is never perfect, but what we need to do is to find a way around it. In this case, what I would say is actually life actually really sucks in this case. You really need to get really creative, hunker down, and get through this. So let's think about what we did in the previous example. In the previous example, we looked at 2 ways. We said, can we partially solve something that will drop an adjacent unit down to 0? Or can we repick a basis? In this case, there is no way you can simply just solve something partially that would drop something down to 0. If you look at this, the overall degree of freedom is the lowest one. So is there something you can do around that so that you drop the overall down to 0? No, you can't do that. The only one you can solve partially, like we looked at before, is we could do a methanol balance and solve for the methanol going into the condenser. But all it does is drop the reactor down to 2. It still doesn't allow you to solve the reactor. So we can't do that. Can we repick a basis? Let's go through this first. There are no subsystems with degree of freedom of 0. Can we repick a basis? And the answer is no. Again, just alone, repicking a basis alone will not do anything. Because in general, you want to repick a basis such that something with a degree of freedom of 1 drops to 0. In this case, our basis is already picked around the overall. So it already involves the overall degree of freedom. Repicking it is not going to drop it further down. You can't repick. You can repick something around the overall, but you lose this one anyway, so you're going to keep it at 1. So the basis is already involved around the system degree of freedom 1 that doesn't help. So this is where we have to get really creative and look at it from both of these ways where we talked about. We need to repick a basis that will allow us to solve some system partially, and then that will allow one of the systems to drop to 0. And in this case, it's just all about looking at the system, thinking about what's going on, thinking about where we can do, get really creative with what we can do here. Again, there are some cases where the degree of freedom, when you have no degree of freedom 0, actually means that you have an underspecified problem, so we can never solve this problem. But in this case, it is not. It's just that we need to be creative here. So we're going to repick a basis that in a subsystem that can be solved partially. And once we partially solve that one, some adjacent subsystem will drop to 0. Where do we pick the basis? Some of the key ways you will want to think about, just strategies to think about, is you want to repick a basis where in that stream you already have most of the information given in there. So for example, in this case, you might think about NF down here because we already know the compositions. If we pick a basis over there, we know every single piece of information in that stream, which usually will be helpful in some way. The other one you have to think about is specifications are usually the equations where they are simple and they involve very few unknowns. And so if you repick a basis that involves a specification, that generally allows you to solve for the specification right away, and so you can solve for some particular system partially. So it turns out that in this case, if we repick NF as our basis, that actually hits on both of these points that I talked about. Number one, we're repicking a basis in the stream where we have the most information. And number two, NF is also involved in our specification. If you remember around the mixing point, we have a specification that says the recycle to the feed stream is 5:1, and that allows us to partially solve the mixing point. And so that is actually what we're going to do. We're going to repick a basis of our feed as 100 kilomoles per hour. Now everything is known down here. Our entry now becomes an unknown. And so now how is our degree of freedom going to change? The overall actually doesn't change because we gain 1 on NF, but we lose 1 in entry. So the overall degree of freedom doesn't change. The condenser has stream 3 coming out of it, so we actually lose a degree of freedom there. So now the degree of freedom goes up to 4. The mixing point goes down by 1 because it involves the feed stream. So now these are the new degrees of freedom. And how are we going to do this problem now? The first thing to do is to solve the mixing point partially. So in terms of solving it partially, we can actually solve all the way about halfway through this problem and actually get N1, NR, and the mole fraction in stream 4 of nitrogen. So what we can solve for is this. We can solve for the recycle and we can solve for stream 1. The remaining unknowns, which are these two and these two around the mixing point, we just don't have enough information to solve yet. But once we get to this point, you'll realize that this YN2 in stream 4, because of this idea of a splitting point, will hit this and will hit this as well. And you'll realize that down here, this is part of the overall system. So once we have that mole fraction of nitrogen in stream 4, it allows the overall system degree of freedom to drop to 0. So you can see we got really creative there in terms of picking a basis, solving something partially, and then using this idea that around the splitting point we have the same compositions. And so even though we did not explicitly solve for something outside, by solving for something inside, it applies to stream 4, the purge stream as well. So next we'll go to the overall degree of freedom. We're going to solve that second, get all the rest of our unknowns. After you have done that, it turns out you have to go back to the mixing point to finish solving the mixing point, or you can go to a splitting point. This is where after you solve the degree of freedom, there's 2 systems that will drop to 0. So you can solve for either the mixing point or the splitting point, finish that up. And once you're done with that, go to the condenser and you're going to solve for everything else. You don't actually need to go to the reactor at all. All right, so let's go through the math really quickly on this. We're going to solve partially the mixing point. Remember, once we have picked the feed as our basis, we can now solve for the recycle stream because the specification gives us a ratio of 5:1. So now we have the recycle stream of 500 kilomoles per hour. Once we have that, we can do an overall balance and we can find the molar flow rate of the stream going into the reactor. So this is simple. It's just NF plus NR, which is 600 kilomoles per hour. The last thing we can solve is you'll realize that everything, the mole fractions of nitrogen is given in every stream. And so that allows us to find the mole fraction of nitrogen in the last stream that we need to. So now we're going to do a nitrogen balance. By doing a nitrogen balance, we only have one unknown left in there, and we can get a nitrogen mole fraction of 0.148. So that is the mole fraction of nitrogen in the recycle stream, which is also the mole fraction of nitrogen in stream 4, which is also the mole fraction of nitrogen in the purge stream. And so with that, that will allow us to drop the degree of freedom for the overall system to 0. In this case, I'm going to solve it using the atomic species method. So if you look at the degree of freedom right here, you will see that what we have solved for is actually this. So now we have 4 unknowns. In the 4 unknowns, we're going to solve it using our 2 reactive atomic species, our inert, and then 1 constraint. So by starting with the inert, our N2 balance, in is equals to out. So we have what we have down here, the overall system, nitrogen is coming in down here, and nitrogen is coming out down here. So we have that. You realize we only have 1 unknown left, which is our molar flow rate of the purge. We can solve for that. Once we have done that, we have our 2 atomic species balances to go. Carbon or oxygen, this is where I'll encourage you to write in terms of carbon, write in terms of oxygen, and convince yourself that you end up with this exact same equation. When you write this equation, we have 2 unknowns in here, so we can't solve for that. Let's do our hydrogen balance. In terms of the hydrogen balance, once again, hydrogen comes in as diatomic hydrogen in the feed, it comes out in methanol, and it comes out as diatomic hydrogen in the purge. So those are the 3 terms we have there. Again, we have 2 unknowns, and these 2 unknowns are not even the same unknowns. So we actually have to solve it concurrently with our constraint. Those are the 3 tools that we have left based on the degree of freedom analysis. Solve 1, 2, and 3 simultaneously, and you can get the 3 unknowns that we need to. All right, once we have this, you'll realize that the 2 systems that drop to 0 is your splitting point and your mixing point. So I'm going to go back to the mixing point first, and then the splitting point, you can do it either way because both of them are at 0 at this point. So we're going to go back to the mixing point. Remember, in the mixing point, we have really these 2 unknowns left, which is the mole fraction of hydrogen and carbon monoxide in stream 1. So we're going to do a carbon monoxide balance, get that, and then we have a constraint to get the other mole fraction, and that's all we have. That's all we have for the mixing point. In terms of the splitting point, it turns out that we actually only have 1 unknown left. We have solved for all the mole fractions. We know the purge. We have solved for everything in the recycle. So the only unknown left is N4. So a simple independent overall balance, in is equals to out, we get our N4. Once we have that, we only have stream 2 that is left that is unsolved for right now, and the one that drops to 0 in this case will be our condenser. So we're going to solve for our condenser down here. Simple in is equals to out for everything that we have there, and with that we end up with our the molar flow rates for all the components we need in stream 2. All right, so what you realize here is that the math is not really the hard part. It's more about how do we even get the strategy correct? How do we outline what are the steps to do it? Like I said, in this case, it's really about getting really creative, moving the basis, solving something partially, and then realizing that, okay, now I finally have a system that drops to 0. All right, we are not done with this question. Remember to always answer the question. Myself included, I have a tendency to, once I finish solving, really just celebrate and be like, I'm done, I've solved for every unknown here. But make sure to go back and answer the question. It wants a methanol production rate of 100 kilomoles per hour. We want the fresh feed rate, the molar flow rate and composition of the purge gas, and the overall and single pass conversions. We re-picked the basis. So our methanol production rate, in this case, did not come out to 100 kilomoles per hour. It came out to 24.32 kilomoles per hour, so we need to scale our entire process back up to 100 kilomoles per hour. The scale factor in this case is 4.11. We need to scale all our molar flow rates up by 4.11 times. So in terms of the actual fresh feed rate, the fresh feed rate in our question was the new basis we picked of 100 kilomoles. So the actual flow rate that we need is 411 kilomoles per hour. In terms of the purge gas composition and the molar flow rate, we'll scale the flow rate up by 4.11 times. So the purge flow rate is 111 kilomoles per hour. recall that when we scale a process up, the mole fractions do not change. So there's nothing to do with the mole fractions. These are what we got from solving the problem, and they're going to be the same even after we scale up the entire process. Then we need to look at the overall and single pass conversions. Single pass conversion is defined as the moles of the reactant that is reacted within the reactor over what you fed in, or in other words, in minus out divided by in. And if you put in the numbers, it's 0.14. Now you realize in this case, I didn't scale up N1 and I didn't scale up this value. You could do that as well, but a single pass conversion is another one of those quantities, just like your mole fractions, that will not change with conversion. So you can go ahead and scale up all these values and go through the math and do the single pass conversion with and without scaling. You'll end up with the same conversion of 14%. The overall conversion, now we're looking at what's coming in the feed and what's coming out in the overall process, in this case in the purge stream. So in minus out divided by in, and we have a 76% conversion. The overall conversion is always going to be higher than your single pass conversion because we are recycling some of the unreacted reactants back in. All right, so one of the questions you might be asking is, wait a minute, how do you know that carbon monoxide is the limiting reactant and you're calculating the conversion based on carbon monoxide? Why are you not calculating it based on hydrogen? In this case, you can go back to the question. If you look at the feed stream and what is actually limiting, it turns out that your carbon monoxide and the hydrogen were actually fed in stoichiometric proportions. So neither of them are limiting, neither of them are in excess. You can yet use either of them to calculate the conversion and you'll end up with the same thing. So that's all we have for this example. Work hard, be smart. We're going to switch gears into chapter 5. We're going to talk about something entirely different before we start to put it back into our material balance questions.